Hey everyone. So in this video I like to talk about inverse cosine and inverse tangent. So, in the last video we said that if we have the function y is equal to sine of x, then the inputs of this function, they represent angles. Whereas the outputs of this function, well, they're going to be y coordinates on the unit circle. And then for inverse functions, well, they reverse the roles of the inputs and the outputs of the original function. So if we have y is equal to sine inverse of x, then the input of this inverse function is not going to be an angle. These are going to be the outputs of our original function. They're going to be y coordinates on the unit circle. Whereas the outputs of this function, these are now going to be angles. And one thing we have to be careful about with these inverse trigonometric functions is that sine, for example, it does not have an inverse for the entirety of the graph. It doesn't have an inverse for the whole function. It actually only has an inverse for a portion of the function, from negative pi over 2 to pi over 2. Right, maybe just to really illustrate this, if we try and take sine inverse of 1/2, well, what does this mean? This is asking us for, this is the y coordinate on the unit circle of 1/2. That's about here is a y value of 1/2. And we can, first off, we can see two different points on the unit circle with a y coordinate of 1/2. Any angle that leads us to either of these points, well, these are angles that give us an output value, a sine value of 1/2. And so inverse sine of 1/2, you might ask, or you might say, well, it should give us any angle that lands on these points. But then that wouldn't be a function, right? Whenever we're dealing with a function, we expect that plugging in a value should only give us one output. And here we're saying, well, maybe this angle, theta is equal to pi over 6, or this angle, theta is equal to 5 pi over 6, or any coterminal angle, like theta is equal to 13 pi over 6. These would all give us y values of 1/2 from our sine function. And so these would all be reasonable angles to expect sine inverse of 1/2 to send us back to. Right, so the question here is, is this pi over 6? Is this 5 pi over 6? Is this 13 pi over 6? And so the solution to this is to make this inverse function truly a function, is to say, hey, we're only going to accept the angles between negative pi over 2 and pi over 2. Those are only going to be the results of this sine inverse function, just to make sure that it's a function. It's not going to give us back any angle that gives a y coordinate of 1/2 on the unit circle in this example. It's only going to give us back the angle between negative pi over 2 and pi over 2. So it's sort of on this right side of this unit circle, and specifically between negative pi over 2 and pi over 2. So it's not going to see this point here. It's not going to see this angle or this 13 pi over 6. Really, sine inverse of 1/2 is only going to give us back pi over 6, not 5 pi over 6 or 13 pi over 6. And so graphically, right, the idea is that here, if we look at this y coordinate of 1/2, it crosses our graph y is equal to sine of x many times, and we're only looking at the portion of this sine function from negative pi over 2 to pi over 2 to define our inverse function, sine inverse of x. So here, maybe just to remind you, or just to say it one more time, is that y is equal to sine inverse of x is only the inverse of y is equal to sine of x for angles between negative pi over 2 and pi over 2. Right, on this interval, the sine function passes the horizontal line test. It's only going to give us one specific value for every given input. And so this is where we've defined our sine inverse function, and this is These are the only outputs we're going to get from our sine inverse function, angles between negative pi over 2 and pi over 2. So let's go ahead and apply these ideas to our cosine function to define a cosine inverse function. So let's look at y is equal to cosine of x. And so the inputs of these functions, just like all of the trigonometric functions, not the inverse trig functions, just trig functions, these are always angles. Right, whereas the outputs of this cosine function, well, these are x coordinates on the unit circle. And one thing I want to point out, just to really make sure we're not confused about this, is that, I know we see a y variable there, but we usually use the y variable to represent the outputs of a function. And so here, that y variable is representing the output of our cosine function, but the outputs of cosine are x coordinates on the unit circle. And so here, if we try and define an inverse function to this cosine function, so y is equal to cosine inverse of x, well, the inputs and the outputs of this function, they're going to swap roles. And so here, the input of our inverse function, cosine inverse of x, this is going to be, these are going to be x coordinates on the unit circle. And the outputs of this function, these are going to be angles. And so one thing we have to be careful about, just like we had to be careful about in our sine inverse function, is that here, maybe let me just illustrate with an example. So if I try and look at cosine inverse of the square root of 2 over 2, whatever this might mean, whatever this might be, well here, this is an x coordinate on the unit circle, the square root of 2 over 2. And cosine inverse, it would give us an angle which corresponds to an x value of the square root of 2 over 2 on the unit circle. But the one issue is that there are many different angles which do this job. Any angle which lies at either of these 2 points, well, these would give us an x coordinate of the square root of 2 over 2 on the unit circle. Right, so maybe just to really give a few examples, right, theta is equal to pi over 4 would be one example. Or any angle coterminal with pi over 4, right? So 9 pi over 4, or 16 pi over 4. Similarly, this angle down here, theta is equal to negative pi over 4, would also give us the same x coordinate on the unit circle, the same cosine value. And so, similarly, another coterminal angle, like 7 pi over 4, or 15 pi over 4, these would all give us the same cosine value of x is equal to the square root of 2 over 2. And so if cosine inverse is going to take this x coordinate and give us back one such angle, it's not going to give us back all of these angles. It's meant to be a function. Cosine inverse is meant to be an inverse function. And it shouldn't give us back multiple answers. It should only give us back one. And so which angle does it give us? Well, here, if we look at the cosine function, right, so it does not pass the horizontal line test. Right, if I look at the square root of 2 over 2 as an output of this cosine function, so this is a height of the square root of 2 over 2, right, there are many different angles which give us this output from our cosine function. And so the idea here is that if cosine inverse is only going to give us one answer, we need to make sure that cosine inverse is going to be the inverse of our cosine function on a part of the graph that doesn't repeat its output values. And so, in other words, we're looking for a part of our cosine graph which is going to pass the horizontal line test. And so one part of our graph which passes the horizontal line test, there are many, but one part that does is this part here. When we look at angles between 0 and pi, our cosine function does not repeat any of its outputs. And so we can define a cosine inverse function for this part of the graph. Right, so any results from our cosine function here, we could apply a cosine inverse function and get back a corresponding angle without any ambiguity. Because there are no repeated output values, there won't be two different input values we can end up at. And so all this to say that the cosine inverse function of y is equal to cosine inverse of x is an inverse function to y is equal to cosine of x. It's only an inverse function to y is equal to cosine of x for angles between 0, oops, sorry about that, 0 and pi. So note that this is different from y is equal to sine of x, which there the inverse function was defined from negative pi over 2 to pi over 2. Here the inverse function for cosine of x is defined from 0 to pi. And so what that means for our picture here is that we're only going to look at angles that fall in this region here from 0 to pi. And so not angles that have walked all the way through the unit circle once or twice. We're just looking at angles between 0 and pi. And so here, we can just ignore all these angles. These are valid angles that give us an output of the square root of 2 over 2 from cosine, but we're just saying that for our cosine inverse function, it's not going to look at all of these angles. It's only going to give us back this angle, pi over 4, because this is the one that's between 0 and pi. So now let's get some practice evaluating this cosine inverse function. And I definitely encourage you to pause the video and try these examples out yourself first if you're feeling ready. But let's go ahead and work through these together. So again, cosine inverse, the inputs of this function, they're not angles, these are x-coordinates on the unit circle. And this cosine inverse function, they're going to give us back angles between 0 and pi. And so here from 0 to pi. And of course this part of the circle, there are many other angles which will land on this top half of the circle, but we're only looking at angles between 0 and pi that land on this top half of the circle when we're dealing with our inverse cosine function. And so what we're doing here is we're looking at the x-coordinate on the unit circle of -1/2. So here's an x-coordinate of -1/2. And we're saying, well, where on our unit circle, what angles give us this x-coordinate? And so, of course, there's many different angles, like we emphasized in the previous examples, but here, maybe I'll just erase the bottom one. I know it's there. There is an angle down there that gives us an x-coordinate of 1/2, but again, cosine inverse is just giving us back the angle between 0 and pi. So I'm just going to draw that top one. So it's giving us back this angle, theta. And so what is this angle? Well, here, this picture, we have a 30, 60, 90 triangle in this picture. And here, this angle to the x-axis, that's 60 degrees. So that makes the leftover angle on the right, theta, 120 degrees, which in radians is 2 pi over 3. And so that's what cosine inverse is equal to, 2 pi over 3. Cosine inverse of -1/2 is 2 pi over 3, because cosine of 2 pi over 3 is -1/2. And this is the angle between 0 and pi that does this job. Okay, so let's repeat this now for arc cosine of 1. And so now remember that we defined this in the previous video, but arc cosine is another way of writing inverse cosine. So this was the case for sine, is that inverse sine can be written as arc sine. Inverse cosine can be written as arc cosine. There's no difference, it's just a different name. And so now we're looking at an x-coordinate of 1 on the unit circle. Well, an x-coordinate of 1 is here. This is x is equal to 1. And so the point on our unit circle corresponding to x is equal to 1, well, it's there on the right. And we're looking for the angle between 0 and pi that gives us this point here. Right, well, the angle that we're looking at is an angle of 0. Right, and at an angle of 0, we're on the furthest right side of our unit circle, and we're dealing with an x-coordinate of 1. And so arc cosine of 1 that x-coordinate is giving us an angle of 0. Right, so here this is 0, an angle in radians. Maybe I should use blue to highlight my answer above, 2 pi over 3. Again, this is an angle output from our cosine inverse function. Okay, let's do the same thing for cosine inverse of 0. So again, 0, that input is not an angle, it's an x-coordinate on the unit circle, and an x-coordinate of 0 is right down the middle, right along our y-axis. This is x is equal to 0. And so what angle on our unit circle between 0 and pi gives us such an x-coordinate? Well, it's this angle here, right? So it's this angle of theta is equal to pi over 2. And 5 pi over 2 also gives us an x-coordinate of 0, but we're only looking at angles between 0 and pi. So here, for this x-coordinate of 0, cosine inverse gives us an angle of pi over 2. So I've got a few more examples I'd like you to try and compute, and when you're ready, we can go over these together. So our cosine of -1, right, this is saying we've got an x-coordinate on the unit circle of -1. X is equal to -1. What angle between 0 and pi corresponds to such an x-coordinate? Well, here, that happens at this leftmost point, and we are at our leftmost point on the unit circle when we're at an angle of pi. So here, our cosine of -1 is equal to pi. What about cosine inverse of, or 2 pi over, or not 2 pi over anything, just 2 pi? Well, 2 pi, I know it's an angle, or it's typically used as an angle, as an input for our trigonometric functions. But here, cosine inverse, the inputs don't represent angles anymore. The inputs represent x-coordinates on the unit circle. And if we looked at an x-coordinate of 2 pi, right, 2 pi, so maybe I'll write here that 2 pi, this is roughly 6.28, so on and so on, right? Pi is 3.141592. 2 pi, let's double that, 6.28, so on, so on, so on, roughly. And so here we're saying this is an x-coordinate. We're asking, if it's an x-coordinate on the unit circle, what angle leads to this x-coordinate? Well, there is no x-coordinate out here. Maybe this should really be way out to the right. We're looking at a unit circle. This is only 1. 6 is going to be really far out to our right here as an x-coordinate. And what angle gives us an x-coordinate of 6.28 on the unit circle? Well, there is no angle that does this job. There's no such angle which gives us an x-coordinate of 2 pi. And so here, this is undefined or does not exist. There's no reasonable angle as a real number angle that does this job. And so this brings up another point that we mentioned when it came to our sine function, was this idea of the domain and range of our cosine inverse function. What makes sense to plug into our cosine inverse function? What makes sense to get out as an output? And so here, this depends on our cosine function, right? Inverse functions, they swap the roles of the x and y coordinates, the inputs and outputs of our function. And so for a cosine, that the domain of cosine in general is from -infinity to infinity. We can plug in any angles we want into our cosine function. We'll always get an output out. But the outputs we get back, they're going to be x-coordinates on the unit circle. And x-coordinates on the unit circle only fall between -1 and 1. And so when we define our cosine inverse function, y is equal to cosine inverse of x, well, the domain of this function, right, they're the outputs of our original function, they're the x-coordinates on the unit circle. Well, those x-coordinates, like we said, they only fall between -1 and 1. So the domain of cosine inverse is going to be -1 to 1. And the range, well, like we said earlier, there are many angles which correspond to these x-coordinates on the unit circle. And we're not going to consider all of them for our cosine inverse function. So here, when we deal with our cosine inverse function, we're dealing with the restriction from 0 to pi. And the cosine inverse function is only going to give us back angles on this interval from 0 to pi. And so that's why when we looked at this cosine inverse function, we only were able to take in inputs from -1 to 1, and this input of 2 pi did not make any sense to plug in. Now what about this next example, arc cosine of -3 pi over 4? Well, here, if we take an inverse function applied to the original function, we would expect them to cancel out, but again, they only cancel out on the defined values of our cosine function, on the defined angles of our cosine function. And that's from 0 to pi. So any angles outside of 0 to pi, well, the arc cosine function and the cosine function aren't going to be inverses to each other anymore. They're only inverses for angles between 0 and pi. These are the only angles for which the functions will undo each other. And so here, if we want to compute this expression, well, let's just work our way inside out. So here, this is arc cosine of, well, arc cosine of -3 pi over 4. Let's evaluate this inside part. Cosine of -3 pi over 4. Let's use our unit circle here. It's going to give us this picture here. So here, -3 pi over 4 as an angle, well, that's in the clockwise direction of 3 pi over 4. Well, I keep drawing this angle wrong. Okay, so 3 pi over 4. That would be here. Theta is equal to -3 pi over 4. Right, pi over 4 is 45 degrees. 2 pi over 4 is 90 degrees. 3 pi over 4, well, that's an extra pi over 4 on top of 90 degrees, so that's 135 degrees. But here in the clockwise direction is what we're looking at because we've got a negative angle. And so here this makes up a 45, 45, 90 triangle. So the side lengths here that we're dealing with, these are -√2 over 2 and -√2 over 2. And cosine is going to give us back that x coordinate on the unit circle. And so here, we're really looking at arc cosine of -√2 over 2. Now again, arc cosine is only giving us back angles between 0 and pi. And so if we look at an x-coordinate of -√2 over 2 like we have here, we're not going to get that angle that's below the x-axis. We're going to get the angle that falls above the x-axis because we're only getting back angles between 0 and pi. So we're going to get this angle here, actually. And this angle is 3 pi over 4 if we're looking at angles between 0 and pi. And so our cosine of -3 pi over 4, this is actually positive 3 pi over 4. Right, so the main idea here is that, cosine of -3 pi over 4, that's a -√2 over 2. And our cosine of -√2 over 2 is only giving us back the angle between 0 and pi, so it's going to give us back that angle on the top half of that circle between 0 and pi, and that's 3 pi over 4. So far, in all of our examples of evaluating these inverse trigonometric functions, the inputs of our functions have always been very familiar values, right? These have all been values from our special right triangles. And when it comes to evaluating inverse trigonometric functions, I do expect you to be able to compute these values from these special side lengths, right? So like √2 over 2, √3 over 2, 1/2, 0 and 1. These are all things I expect you to be able to compute as an input to our inverse trigonometric functions. But the moment we have an input that's not one of these special values, we do have to resort to using a calculator. And so here, let's take a look at these two examples down here. So cosine inverse of -2 over 3. So here, we can also, despite having to use a calculator, we can still make sense of what we're doing when we evaluate something like this. What we're looking at really here is an x-coordinate of -2 over 3, right? Cosine inverse takes in an input of x-coordinates on the unit circle, and so here we're saying add an x-coordinate of -2 over 3. What's the angle between 0 and pi? So on the top half of this unit circle, what's the angle between 0 and pi that gives us such an x-coordinate? And so here we're looking at this particular angle, so this angle of theta here. And so when we evaluate this using a calculator, we get an approximation. It's not an exact value. And here we end up with a value of 2.3005, so on. So I'm just going to write 2.3. And that should make sense because pi, right, this is approximately 3.1415, so on. And our angle here is pretty close to halfway around this unit circle. So 2.3, that's pretty close to 3.14, so it makes sense. But again, our result here, it's an approximation when we use this calculator to get this really long decimal value that we're cutting off at 2.3. And the result of this function, as it was the case for all of our previous examples, the result of evaluating this function, that's an angle, which gives us here in this case an x-coordinate on the unit circle of -2/3, because we're dealing with the cosine inverse function. Now when it comes to the sine inverse function, or arc sine, here we're not looking at an x-coordinate of 4/5, we're looking at a y-coordinate of 4/5. And so here I have to erase this picture and redraw everything, but here we're looking at a y-coordinate of 4/5, so that's pretty close to a y-coordinate of 1. And there's two different positions on our unit circle which give us such a y-coordinate, which sine outputs such a y-coordinate of 4/5. But again, sine, arc sine, is going to give us back angles between -pi/2 and pi/2, because that's where our function sine passes a horizontal line test. And so here we're only going to get angles between -pi/2 and pi/2. And so here we're going to end up with this angle here. And again, we're not familiar with sine well enough to get the angle directly, the exact value that corresponds to a y-coordinate of 4/5, but we can use our calculator here in this case to get an approximate value. And this gives us approximately 0.927. And this should make sense because, here, this was a little more than 3 radians, right? Pi radians. Earlier we drew a picture where we had a little bit more than 2 radians, and so here this kind of makes sense that it's a little bit less than 1 radian. Right? So 1 radian is about 57 degrees, and that feels about right? Pretty close to 60 degrees. And so here, our output to our arc sine of 4/5, that's 0.927, and this is an angle which gives us roughly a y-coordinate of 4/5. And now one thing I want to warn you about when it comes to using a calculator to evaluate trigonometric functions and inverse trigonometric functions is you always have to be careful of the mode in which your calculator is in. So here, we want to make sure that we're in radians mode, and here, right, our results are in radians, and we kind of related them to, pi radians, and so here they kind of make sense in this picture, and we've kind of checked our work a little bit. But if you're in degrees mode and you're intending to get radians as a result, you'll get answers that are way off. And so, it's a good idea to have a sense of where the number of radians are along this unit circle, just so that you can check your work and make sure that you're not accidentally getting answers that are in degrees.